Well, welcome back. We're now in section 4.5. And 4.5 is called optimization. This is one of those huge sections in terms of your Calculus 1 career that we really hit you hard on. And so you can anticipate lots of questions on this stuff on the final exam. So really get this material down. Section 4.5 is on optimization. There's two major word problems that we really focus on in terms of Calculus 1, and that is the related rate problems that you guys did in chapter 2 actually, chapter 2.7, and optimization, section 4.5. Major word problems is what this stuff's about. So, the idea of optimization, we're going to be looking at word problems, and we're trying to figure out when to maximize something or other, or when to minimize something or other, the optimal points of these particular problems. So, the big setup is this. So I try to type up for you guys basically the 6 steps to glory of how to do an optimization problem. All right, and for most problems, these steps will work. If you got an easier problem, you don't even need as many steps. But here's the deal. Steps involving word problems. Dealing with optimization. You have to, number one, read a problem, draw a picture and label it, because you're going to have to get some major word problem. You got to see what's going on, draw the picture, what's going on, and label it. Then come up with the objective equation. Now, what I mean by objective equation, you are supposed to maximize volume, minimize surface area, minimize cost, maximize the profit. You're trying to find something big or small about the problem. That's the objective equation. The objective equation, now this is Calculus 1. The objective is to take derivative, set it equal to 0, and solve. And that's going to be the equation that you're going to do that to. But in each problem, they're going to give you some kind of constraint, some kind of special relationship about the problem. That's called a constraint equation. You're going to have to take those variables in that picture and come up with what they tell you as a constraint equation. They give you some kind of constraint, and you're going to make an equation out of it. So what you're going to do then is take the constraint equation and solve for one of the variables and plug it into the objective equation. Because usually the objective equation has too many variables in it. You know, the volume of something or other is maybe x squared times y. Well, I got 2 different variables in there. Well, that constraint equation that they give me, some kind of constraint about something or other, is going to be some kind of equation with x and y in it. So I'm going to solve for y in terms of x, plug it into the objective equation just to get that objective equation in terms of one variable. Because step number 5, that's your money maker. Well, how do you maximize or minimize anything? You take derivative of the objective equation, set it equal to 0, and solve. And compare it to the constraints. Now, keep those constraints in mind because they're the link between the x and y. And then the last thing you ever do to these word problems is go back and make sure you answer the question they ask. So here's a couple of examples and ideas that we're going to put on these pre-Moodle quizzes. And here's the first one. Given this function, f of x equals 16x divided by x squared plus 16, what is the maximum value of the function? Trying to get this idea about maximizing, minimizing was what these optimizations all about. To maximize or even to minimize, I'm going to take derivative, set it equals 0, and solve, and where the derivative doesn't exist at. How do I take derivative of this guy? Well, I got 16x divided by x squared plus 16. I'm clearly going to use the quotient rule. Quotient rule, drill the top, 16 times the bottom, x squared plus 16, minus the top, 16x times drill the bottom, 2x, all over the bottom, x squared plus 16 squared. Okay? Now, let's clean this guy up. This is equal to 16x squared plus 16 times 16, using my old handheld calculator here, 16 squared is 256, minus 16 times 2, that's 32, x times x is x squared, all over that bottom squared, x squared plus 16 squared. I can combine like terms up there. What is 16x squared minus 32x squared? That gives me my derivative to be equal to 16x squared minus 32x squared is minus 16x squared plus 256 divided by x squared plus 16 squared. I'm going to set my derivative equal to 0 and solve, and by multiplying both sides by my common denominator, which is x squared plus 16 squared on both sides. When I cancel, this cancels here, leave me with negative 16x squared plus 256 is equal to 0 times anybody is 0. Solving for x, I'm going to solve for the x squared first, so I'm going to subtract 256 from both sides. That gives me negative x squared equals negative 256. I'm going to divide by negative 16 on both sides, and that gives me x squared equals, now here we go, we got a negative divided by negative is a positive. 256 divided by 16 is actually 16. And then I'm going to take the square root of both sides, but officially I need to take the plus or minus anytime I do square root. So the answer I get is x equals plus or minus 4. Okay, this is my CN, as we discussed before, the critical numbers, where my derivative is equal to 0, plus or minus 4. Now, I also have to worry about where the derivative does not exist at, but the denominator, when you set it equal to 0, will never be equal to 16 because it's a plus. You take a number and square it, it's positive. Add 16, it's more positive. Square it's even more positive, so you never get it to be equal to 0. So the derivative always exists, and all I have to worry about is my critical numbers are at negative 4 and positive 4. The question is, which one is the maximum, which one is the minimum? Well, the only way you do that, now we're going to go after the critical point. So I got x is negative 4, and I got x is positive 4. So now I'm going to type in or plug into my equation, my original equation. I'm going to get the y coordinate, plug into the original equation. So I'm going to plug in negative 4. So 16 times negative 4 divided by negative 4 squared plus 16. And just double check me on this one and make sure you get the same number I got. But when I plugged in negative 4, I got negative 2. And when I plugged in positive 4, I got positive 2. Now, answer the question. Which one has the max value? We discussed this before. The idea of value is the y coordinate and maximum with the biggest y coordinate. So between the two, which one's the biggest y coordinate? It's clearly the positive 2, so the maximum value is positive 2. So you got to find your critical numbers by taking derivative, set it equals 0 and solving it, and then take those critical numbers and plug them into the original function to get those y coordinates. And remember, the one with the biggest y coordinate is the maximum value. The one with the smallest y coordinate would have been the minimum value. So let's take a look at this particular problem here and see if we can answer this one. Find two numbers, a and b, with a less than or equal to b, setting you guys up for web work, whose sum is 56 and whose product is to be maximized. Well, I'm going to go through, this is the beginning of your word problem, so I'm going to go through kind of my steps here. You're supposed to read problem, draw a picture, and label it. Well, find two numbers, a and b, with a less than or equal to b, whose sum is 56 and whose product is to be maximized. Well, there's no really, so I got two numbers. I got a number, this will be like the first number, and I got a b number, the second number. Nothing really to draw here. But whose sum, a plus b, is 56, and whose product, what do we mean by the product? The product means multiply the product of the two numbers, a times b, is to be maximized. This is the guy we want to maximize. So in terms of objective equation, the equation we want to take derivative of, set it equal to 0 and solve, because that's our objective in life being calculus students, is the product equation. Product, we'll call it P for product, is a times b. The constraint equation is the equation with the given information that links my two guys together, which was the equation a plus b equals 56. Now, what I'm going to do here is take the constraint equation and solve for one of the variables. I'm going to solve for b. b would be equal to 56 minus a, and I'm going to plug it into my objective equation. This is going to give me my objective equation to be product equals a times b, but b equals 56 minus a. The point in doing all this stuff is to get that objective equation in terms of one variable. See, I've got too many variables here. I got a and b, but when I take the constraint equation and solve for one of my variables and plug it in, that gives me my objective equation to be 56a minus a squared when I distribute. Now, calculus. Take derivative, set it equal to 0 and solve. So my derivative of my product would be derivative of 56a is 56 minus derivative of a squared is 2a. Set it equal to 0 and solve. This gives me 56 equals 2a divided by 2 on both sides, and that gives me a to be equal to, like I said, 56 divided by 2, which is 28. Okay, but the last step, and really what I'm trying to do here is kind of mimicking this step here, is go back and answer the question. We're supposed to find two numbers whose product is to be maximized. So the two numbers is A has to be equal to 28, and therefore B has to be what? Well, to figure out what B is going to be, go back to the constraint equation. That's your linking equation between the two variables. B was equal to 56 minus A, so that would be 56 minus 28, which actually equals 28. So to maximize, they got to be the same number for that product here. So the answer is A is 28 and B has to be 28. Go back and answer the question after you take derivative, set it equals 0 and solve. So one more problem here. Take a look at this guy. And here's your classic, and then we're going to be doing more and more and much harder problems throughout the section 4.5 optimization, but here's a guideline. Here's a classic one right here. Farmer Brown has 16,000 feet of fencing to create a rectangular pen that will be adjacent to a river. If he does not need to put any fence on the side that borders the river, what dimensions will maximize the area of the pen, and what is the maximum area? So classic word problem. And this is what students get frustrated about to no end. So give you guys the steps. So 6 steps to glory. Step 1, read the problem. Farmer Brown has 6,000 square feet of fencing to create a rectangular pen. So draw pictures. Rectangular pen that will be adjacent to a river. So here's going to put the river over here. So here's my river. Okay. If he does not need to put any fence beside the river, so we're going to put the fencing here, here, and here. Obviously, we'll put the cows, get down to the water or whatever. So we're only going to put fencing on 3 sides. And so in terms of, we want to figure out what the maximum area has to be. So in terms of labeling it, I'm going to call this side X. So this side will also be X, but it's a rectangle. So this long side will be different. I'm going to call it Y. So step 1, read problem, draw a picture, and label it. Step 2, come up with the objective equation. What's my objective? We are supposed to maximize the area. So the objective is that we want to do is we want an area equation, because that's the guy we want to take derivative of, set it equals 0 and solve. Now we're going to use some of your math skills. I have a rectangle. What's the area of a rectangle? Length times width. That'll be X times Y. Okay? This is my equation called the objective equation. I want to take derivative of this guy, set him equal to 0 and solve. The objective is to maximize area. Problem is it's too many variables. I only want this stuff in terms of one variable. So the next step I got to do is come up with the constraint equation. My constraint is the fact that they gave us 6,000 feet of fencing. We got 6,000 feet of fencing. Now, we've got to create an equation out of this. Well, where are we putting fencing at? We're putting it over here with this X, we're over here with this Y, and this X. That's 2 X's and 1 Y. So 2X plus Y has got to be equal to that 6,000 feet of fencing. Here's my constraint equation. Step 3, solve that constraint equation for one variable. Easiest is to solve for Y. Y would be equal to 6,000 minus 2X. And then take that constraint equation and plug it into the objective equation. That will give you the objective equation area to be equal to X times 6,000 minus 2X. So cleaning it up, area equals 6,000 X minus 2X squared. Now we're supposed to maximize this guy, maximize the area. So to maximize or to minimize, you take derivative, set it equals 0 and solve. Well, the derivative of area, or derivative of 6,000x is 6,000. Minus derivative of 2x squared is 4x. Set it equal to 0 and solve. Adding 4x to both sides, this gives me 6,000 equals 4x. Then I'm going to divide by 4. That gives me x is equal to 6,000. Divided by 4 is 1,500. Now, don't forget to do this. Last step, step number 6. Go back and answer the question. Well, this one they had 2 questions here. What were the dimensions that maximized the area of the pen? Well, the dimensions of the pen are x by y. Well, I know what x is. That should be 1,500 feet of fencing. Okay? And now, so my dimensions are x by y. So now I need to figure out what y is. To figure out y, go back to the constraint equation. You went solve for y. Y is equal to 6,000 minus 2x. So y would be equal to 6,000 minus 2 times x, but x was 1,500. So 2 times 1,500 is 3,000. 6,000 minus 3,000 is 3,000 feet of fencing. So the dimensions are that will maximize the area of the pen are 1,500 feet by 3,000 feet. Okay, but there was one more question. The other question is, what is the maximum area? The max area, you can go back to the original area equation, which was x times y, and plug it in. That'll be 1,500 times 3,000. And 1,500 times 3,000 is 45,000,000. I'll let you know, I really did just type it in on my calculator there. There you go, you can see it. 1,500 times 3,000 is, so there are 5 zeros there, so 1, 2, 3, 4,500,000 feet squared. Feet by feet is feet squared. That would have been my maximum area that I would have for my cows to be down in the pen or whatever. But pay attention to these 6 steps and how to go from word problems down to final solutions. Step 1, read the problem, draw a picture, label it. Step 2, come up with the objective equation. That's the equation that you want to maximize or minimize. The equation you're going to eventually take derivative of, set equals 0 and solve. Come up with the constraint equation. Equation that links the 2 variables together. Solve the constraint equation in terms of 1 variable and plug it into the objective equation. Clean them up, take derivative, set it equals 0 and solve, and then go back and answer the questions. Those are the major steps on this particular section 4.5. So study hard, and I'll see you on the next video.